So if we look at this one, first of all, how do we find angle A, big A here?
90 plus 29.
90 minus 29, which makes it 61 degrees, right? Now, again, I want to use the 29 because that was given. I know it's right. And even though we're absolutely confident of the 61, there's a small chance we might have screwed up. So let's just stick with the 29 because it's given information. To find A here, 21 is what side compared? First of all, it's the opposite. Very good. And A, when we're looking for A, that would be the adjacent. So we have opposite and adjacent, which is tangent. So I'm just going to write it out. Tangent of an angle is opposite over adjacent. And I'm going to fill in what I know. Do I know the angle?
Yes.
Yes, I do. So tangent of 29. Do I know the opposite side? Yes, 21. Adjacent side is A. That's what we're looking for here. So I'm going to put this over 1, cross multiply. 1 times 21 is 21, divided by tangent of 29. .89 millimeters. How many of you got that? Cool. How many of you didn't get that far? Now then, to find C. We still have the 21, which is the opposite. C, of course, would be the hypotenuse, which is going to be the sine. Sine of x is opposite over hypotenuse. And again, we fill in our information. Do we know x? Do we know the angle? Well, yeah, it's still 29 degrees. The opposite is still 21. And the hypotenuse is C. So we put this over 1. Now it's 1 times 21. This time it's divided by the sine of 29. 43.32. You got it. And, of course, if we wanted to double check, we do a squared plus b squared equals c squared, right? Well, I'm going to do this. I'm going to do the square root of 21 squared plus 37.89 squared. This better come out really close to 43.32, and it does. So we're good. We're golden. Oops, I don't know where that came from. Something like that, yeah. So on this one, find angles A and B and then side little a. Okay. Now, of course, side little a you could find here with a squared plus b squared equals c squared if you wanted to. In fact, let's do it. Whenever we have two sides, that's generally the most effective way, the simplest way to find it. So it's going to be the square root of 2.6 squared minus 2.3. Why did I subtract? Yeah, because the 2.6 is hypotenuse. Very good. So you get 1.21. That'll be inches. So little a is 1.21 inches. No use getting into the trig when I've got the Pythagorean theorem there. Now for angle, big A, of course, the 2.6 is the hypotenuse. 2.3 would be adjacent. So hypotenuse and adjacent is cosine. Cosine of an angle is the adjacent over the hypotenuse. So now in this case, when I go to fill in these numbers, do I know the angle? No. So it's angle A, so I put A in there. Do I know the adjacent side? Yep, 2.3, and the hypotenuse is 2.6. If I don't know the angle, I better know both the sides. Now this is different. When I'm missing one of the sides, like up here, when I was missing one of the sides, that's where I do put it over 1 and I cross multiply and divide. When I'm missing the angle, it's different. When I'm missing the angle, that's when I do the inverse cosine of 2.3 divided by 2.6 in parentheses. So I'm going to do second cosine. I'm using the second button, not the x negative 1 key. 2.3 divided by 2.6, close the parentheses. Oops. Write the 2 in there. 0.80, perfect. Now I could go back and use the sine for angle B if I wanted to. I'm guessing it'll come out to 62.20 degrees. That would be the sine of B is going to equal to 2.3 over 2.6. Inverse sine, second sine, 2.3 divided by 2.6. Magically it is 62.20. So the question comes, why do we care about finding these missing sides of triangles? Well, because you're going to have to do it a lot. Let's look at some reasons why you might do it. An application that used to be huge is not quite as much as what it used to be because now we've got adjustable bevels and stuff like that. Was the sine bar. What do you guys have for a sine bar down in the shop? Have you used one at all?
Not yet.
Not yet? Do you have a 5-inch or a 10-inch? Do you know? A 5-inch? Well, they have 5 inches and 10-inch ones. They're both pretty common, but the 5 is probably slightly more common just because it's smaller. So anyway, don't know why that one disappeared. So a sine bar, what it is a very precisely made bar. It has these rounded ends on it. The reason the ends are rounded is so that it can sit, and yeah, exactly, so it can tilt at any angle. From the center of this circle to the center of this circle is an exact dimension. Now, as you said, you guys have 5-inch ones down in the shop, so it's exactly 5 inches from center to center. And like I said, those are very precisely circular, so that even if it's sitting like this on top of something, from this point of contact here to this point of contact here will be exactly 5 inches, period. So,
Wherever it's tangent.
Yeah, wherever it touches, wherever it's tangent, wherever those round surfaces are tangent. So, I mean, it is very precisely done. The sine bar historically has been used for creating angles. So if I want to create a certain angle here, right here, I'm using my 5-inch sine bar, so that means the hypotenuse of my triangle is going to be 5 inches. Normally what we're trying to find is this over here, the opposite side, the vertical. This is going to be created with gauge blocks. I know I spelled that wrong. But you know what I'm talking about, right? Anyway, it's going to be built up precisely with gauge blocks. And you remember, gauge blocks can get down to a 10,000th of an inch. So let's say that we want exactly, let's do a 22-degree angle here.
Before you go any further, Todd,
Yep.
explain this to me. I understand how it works, and I understand the gauge block. What's the purpose?
What's the purpose?
Yeah, give me a situation where I'm going to build up my gauge blocks to a particular height for whatever the angle is.
Okay.
Give me a reason. I'm making what?
The main purpose of the gauge blocks is to calibrate your instruments, your quality control instruments, calibrating your calipers, your micrometers, and all that stuff. Something like this would be if you're in a production setting, you're going to have a jig of some sort, a fixture of some sort that is made to have that angle, so you're not going to need to build it up. Most of building up the gauge block buildup is when you're doing the tooling. So let's say you are creating the tool, or you're creating that fixture that's going to be sitting there. So you've got to have a precise angle on that fixture. You're going to be doing this. Production setting, no, you're not going to have gauge blocks sitting there because gauge blocks are unstable in the long run. But for making the fixtures themselves in the tool shop. And right now, that's where the big money is.
Right.
I worked for a short period of time in the injection molding industry. Tell you what, even a small injection mold, you're looking at 12 grand to have that sucker produced. So there's some big money there.
So this is more or less to produce the jigs, make
Yes.
the jigs or the work molding.
Either making the tooling itself or custom order.
Right.
Yeah. So let's say we need that 22-degree angle there. So what we have here, of course, this is the opposite side, and the sine bar, the length of the sine bar, is always going to be the hypotenuse. Guess what trig function we're going to use? Sine. That's why it's called the sine bar. So the sine of our angle, I can't put x in there now, can I? The sine of our angle is equal to the opposite of our hypotenuse. So I'm going to put in the sine of 22 degrees is equal to x over 5. Now again, we have two choices. Either we're looking for one of the sides or we're looking for the angle. If we're looking for the angle, that's when we just use the inverse trig function. Here we are looking for one of the sides, so we put this over 1 and we'll cross multiply and divide. Well, this would be the sine of 22 degrees times 5 divided by 1. So just sine of 22 degrees, make sure we close the parentheses, times 5. 1.873. Now, when we're using a sine bar and doing a gauge block buildup, we do want to go to at least 1/1000th of an inch, if not 1/10,000th. So that would be 1.8730 inches in this case. Now, many times, we want an angle a little bit more precise than 22 degrees. What if we want an angle here that is 18 degrees, 40 minutes? Well, we can still enter this. 5-inch sine bar again. Sine of our angle is opposite of our hypotenuse. If we let x be our opposite side, that's the height we're looking for. Sine of 18 degrees, 40 minutes equals x over 5. Have all of you figured out how to enter 18 degrees, 40 minutes in your calculators yet? Is there anybody that has the old one-line display? So no. You have, yours is a 2-line, so you've got that degree, minute, second button there. So you're going to enter sine 18. Now I've got an angle key on here that does it all for me.
I can't remember what.
You've got a degree, minute, second button there.
Yeah, I know, of course. Oh, I got an angle button.
That's what it was, yep.
Okay, so then
So second angle
close that then.
minutes. Yep, close that. So you got sine of 18 degrees, 40 minutes, and then times 5. You get 1.6003.
Yep.
What do you guys think?
Not bad.
Not terrible? Okay. The other side of it might be if you come across a fixture that's set up and you look at the gauge block buildup here and you see that gauge block buildup, this is a 5-inch sine bar again, and you see that gauge block buildup is at precisely 2.1374 inches. And you need to figure out, well, what angle are we using here? Well, if that's my angle, again, our function is going to be sine of an angle is opposite of our hypotenuse. So we don't know the angle. That's x. That's what we're looking for. Opposite is 2.1, or opposite is 2.1374. Hypotenuse is 5. Now this time, since we're looking for the angle, it's going to be the inverse. So second sine of 2.1374 divided by 5. Second sine, 2.1374 divided by 5. Yep, divided. I get Ooh, I did that wrong. Second sine 2.1374 divided by 5. 25.31 degrees, yep. Now, if we want it in decimal degrees, that's fine. Or we can switch it into DMS. That'd be 25 degrees, 18 minutes, 28 seconds, basically. Other applications. When we have a taper, there are three common features of the taper that we're familiar with. We have the large diameter, the small diameter, and of course the length. But there is a third dimension, or fourth feature that we sometimes talk about. It's the taper angle, right there. To find that taper angle, we are literally just constructing a right triangle here. There's our right angle. This, of course, is the length. This here, of course, is half of the difference in diameters. Why is it half the difference? Well, because what it is the difference in the radii. And the radius is half the diameter for each. So you could divide each diameter by 2 and subtract them if you wanted to, if that's simpler for you to comprehend. Let's put some numbers in here, Jason. Maybe it'll be clear. Let's say this is 1.2 inches here in diameter. And this is 0.8 inches in diameter. To find this dimension right here, I need the difference in the radii, in the radius. So it's probably easier is to divide this to find a radius. This would be a 0.6 inch radius. And this would be 0.4 inch radius. So then this dimension here is the difference between 0.6 and 0.4, otherwise known as 0.2. And let's say that this is, I don't know, 6.3 inches. So that means I have this triangle up here where this is 0.2 inches and this is 6.3, and I'm looking for this angle. Right now what I have is both legs. This is the adjacent, this is the opposite, which means I'm going to be working with a tangent. Tangent of an angle is opposite over adjacent. Now I know the opposite side is 0.2, the adjacent side is 6.3, so this is going to be an inverse tangent. So second tangent, 0.2 divided by 6.3. I get 1.82 degrees. Here's my taper angle. Not so bad. Other applications. This one kind of ties in our circle stuff along with all this good stuff. You know how to figure it out? Well, this angle down here is going to be 60 degrees for this example. This is going to have a radius of 0.8 inches. Let's say that this here is 1.1 inch. And this here we're going to call 2.4 inches. What I want to know, how far does my ball stick up above the top of the V block? So what I really need to find here is this dimension right there. I know this dimension is going to be, well, we'll come back to that. Don't worry about it. Let's find it.
You just make a right triangle right there.
Yep, I'm going to put my radius in here.
There, you know, that's a 90.
Yep.
Okay, you got one of your legs there and your angle.
This angle here is going to be what? 30, half of the 60.
Yep.
Perfect. So what we have is we have right angle, 0.8, and 30 degrees. We have the opposite side. We're looking for this one here, which is hypotenuse. Opposite and hypotenuse are sine. I write out my definition, and I'm going to plug in sine of 30 degrees equals 0.8 over the hypotenuse. So I'm going to put this over 1. 1 times 0.8 divided by the sine of 30 is 1.600, correct? So this is 1.600 inches. I'll pause. Everybody get that? No? So on your calculator, you got 1 times 0.8 divided by the sine of 30. Divided by the sine, not times.
Yeah, 1.6.
1.6.
Plus your 0.8.
So we've got 1.6 plus we do have another 0.8 here. Plus 1.1 here. If we add that all up, we're going to get a total height from here all the way down of 3.50, right? Subtract the 2.4 from here. This is 1.1. What do you think?
Yeah.
Better than a sharp stick in the eye? What's that? That hurts.
Cool. Didn't you say all our V-blocks in the shop are 90 degree angles?
Yeah.
Yeah, but that's no fun.
It's easy.
We don't know what the angle is, no. Find that angle. So here's what we do. We know this is how much? 0.6. With that information, can we find this dimension right here? Okay, because we got 2.8 here total. Minus 0.6 and 0.9 leaves us with 1.3 inches total from there to there, correct? Which means, obviously we know that this radius is 0.6. So we can find this angle here. I'm going to call that angle X. We have the opposite and the hypotenuse, which is sine. So I'm going to fill in. I don't know the angle. What I'm looking for is I'll call that X. I have 0.6 over 1.3. So I'm going to do an inverse sine of 0.6 over 1.3, or 0.6 divided by 1.3. Second sine, 0.6 divided by 1.3. 27.49. And now, of course, that's half of our angle, so we have to times 2. So 54.97 degrees. Not so bad? Cool. another application for us. I'm going to cheat here for a second. Pretend that's a circle.
You don't have to.
It's a freaking circle.
It's a bear.
It's the reason you're going to take this class again next year.
Green.
Pretend those holes are equally spaced around that circle. Holy crap, they're not even close.
Just add one.
On my computer screen, they look kind of close.
It's like diameter.
Give me some time, man. Demanding, aren't you? You guys paid to take the class. You think I should be at your will. I'm going to leave off the extra zeros. It's a 1.8 inch diameter. What I want to know, if these are equally spaced, I want to know center to center distance between holes. Well, we do know that this length here is 0.9 inches. Where did that come from? Half the diameter. That's a radius. How'd you get that?
Because you take 5 divided by 360.
Okay, you did it correct. You just said it wrong. Yeah, 360 divided by 5 is 72 degrees. Yeah. Perfect.
Whatever, I need the answer.
So now what I'm going to do is I'm going to cut that in half because there's no right triangle in there anywhere. But if I cut that in half, of course, it cuts this in half and cuts this in half. This is 36 degrees. So what I have there is a triangle, a right triangle, that is 36 degrees and 0.9 inches. So what I have is I have the hypotenuse here. I'm looking for this piece. I'm going to call this y. That's the opposite side. So, of course, I'm looking at the sine of an angle is opposite of our hypotenuse. I always write those definitions out. That makes sure I get everything in the right spot. So, sine of 36 degrees equals the opposite side is what I'm looking for over 0.9 is my hypotenuse. Cross multiply and divide. So it's sine of 36 times 9, or times 0.9, I should say. And we can deal without dividing by 1. So I get 0.529. So y is 0.529. Is that the answer I want?
No, you got to times it by 2.
You got it.
The triangle.
You got to multiply by 2 because it was half. You are correct, sir. Cody's on a roll today. 1.058. So that's 1.058 inches between the holes. So anyway, in the packet I gave you guys yesterday, page 358 to 361, there's a ton of these applications. I'd start out by doing the odds. If you're struggling, go back and do the evens. The hard part is usually picking out where the right triangle is. You notice in this last one, there was no right triangle. We had to create it. The first couple of examples we did, the right triangles were pretty obvious. You know, the V block, whenever you see a circle up against a straight line, you know there's going to be a tangent, so you know that's where your right angle is. The whole spacing is a little tougher to find the right triangle, but that is the trick, is to find the right triangle.